No, but it's just for introducing the session. Then I will give this to the speakers. So I am again Giuseppe Caire. Welcome to this afternoon session. We have 4 talks, and the first talk will be given by Uzi Pereg. Right? Did I pronounce correctly? Okay.
Yeah. Thank you. Thanks for the introduction. Okay, just a second. Okay, so this is a joint work with my advisor, Yossi Steinberg, on the arbitrarily varying relay channel with sender frequency division. Okay, so this combines 2 models, the Gaussian relay channel with sender frequency division, we'll see what that is, and the arbitrarily varying channel, the AVC. Okay, the relay channel was introduced by van der Meulen. It is considered to be a fundamental building block for communication networks. Okay, here we have a very simple network of 3 nodes where the sender wishes to send information to the destination receiver with the help of the relay. Okay, the relay receives the noisy version of the sender's transmission and sends its own transmission to the receiver with the purpose of helping the sender's communication. Okay. Now, El-Gamal El-Zahedi introduced the relay channel with orthogonal sender components. Okay, here the input consists of 2 components. One is sent directly to the destination receiver, and the other is sent through the relay. Soon we'll talk about the Gaussian relay with sender frequency division, which is a special case of the relay channel with orthogonal sender components. Okay, as for the AVC was introduced by Blackwell, Brayman, and Thomasyan as a model for a channel with unknown statistics that may change over time. This is the case, for example, when there is a jammer who randomizes the state sequence in order to disrupt communication and maximize the probability of error. And it is also relevant for modern networks such as biometric secrecy system attacked by a hacker using an optimal jamming strategy. Recently, there's been a lot of interest in the Gaussian relay channels, all sorts of models on Gaussian relay channels. This is a very partial list of papers, and one of the cases is the case of sender frequency division, okay, which is, as I said, a special case of the relay channel with orthogonal sender components. So now we give a bit of background. We start with the AVC. Blackwell, Brayman, and Thomasyan determined the random code capacity of the AVC. That is the capacity achieved by stochastic encoder, stochastic decoder coding scheme when there is shared randomness between the encoder and the decoder. And they also showed by example that the random code capacity may not necessarily be achievable using deterministic codes. Okay, and then Alswed showed that the deterministic code capacity has what we call a dichotomy property. Dichotomy property means that the capacity is either 0 or it equals the random code capacity. When I just say capacity, I mean deterministic code capacity. Okay, and then Ericsson and Chizar-Narayan established a computable condition to verify whether the capacity is positive or 0. Okay, they showed that the capacity is 0 if and only if the AVC satisfies a property called symmetrizability, if it is symmetrizable. Now, a network can also be attacked by a jammer, of course. So there's a line of papers on arbitrarily varying networks, including the arbitrarily varying multiple access channel, broadcast channel, wiretap channel, and we've recently introduced in the last ISIT the arbitrarily varying relay channel, which we're going to talk about a special case today. Okay, so now to our main contributions in this work. We considered the arbitrarily varying Gaussian relay channel with sender frequency division. We determined the random code capacity. We developed lower and upper bounds on the deterministic code capacity. Then we also considered the arbitrarily varying primitive relay channel. First, the general case, we give lower and upper bounds. And then the Gaussian case, we determine both the random and deterministic code capacities. Now, our proof technique extends the techniques of Chizar-Narayan in the 1991 paper specifically on the Gaussian AVC. Okay, they have a paper on that, and we're also going to use our results, our previous results. Okay. So now we begin with the definitions. Okay. Here the relay receives this sequence, Y1, which is X double prime plus Z. The output of the channel is X prime plus X1 plus S. Okay, so let's go through it. Okay, X prime and X double prime are two components of the input. Okay, the input consists of two components, X prime and X double prime. As I said, Y1 is received by at the relay, and X1 is the relay's transmission. Okay, Z is a independent Gaussian noise. Okay, and this S is the state sequence. For an arbitrarily variant channel, the state sequence has an unknown joint distribution, not necessarily a memoryless distribution. It could even give probability 1 to a specific state sequence, so it includes the case of a deterministic unknown state sequence. And since it is a Gaussian channel, power limitations must be accounted for. So the transmitter has this input constraint omega, the relay has the constraint omega 1, and the jammer has the state constraint lambda. Okay, so here as the channel looks like this. Okay, the relay receives Y1 X prime plus Z and sends X1. And the missing part here is the relay encoder. Okay, the relay uses a strictly causal mapping F1I, where in time I the relay uses only the sequence of past received symbols. That is Y1 from time 1 to time I minus 1. Now, a random code is defined as the triplet of these two encoders and decoder drawn at random from a given collection of codes with shared randomness between those three parties, between the two encoders and the decoder. So now we give a brief review of related work. So first we look at the AVC without a relay. The Gaussian AVC specified by Y equals X plus S plus Z, Z Gaussian, and we have the same constraints omega and lambda. Okay, so using our Rayan showed that the random code capacity is given by this formula. Okay, here we have the variance of the interference is the combined variance of the jamming power lambda and the noise variance sigma square. Okay, so some may say that this is not a very surprising result. Okay, but now that we look at the deterministic code capacity, Chizar and Ariane showed that if the input constraint is greater than the state constraint, then the capacity is the same as the random code capacity. However, otherwise, it is 0. Okay, here we have this figure, the capacity as a function of the input constraint. So the dashed line indicates the random code capacity, and the solid line indicates the deterministic code capacity. So we consider that the capacity is discontinuous in the input constraint. This may seem strange because what happened to time sharing, right? Time sharing is impossible for the AVC under a state constraint because if you use a code over a shorter subsequence of the block length, then it effectively increases the state constraint. Now we note that this is a dichotomy property, but it does not follow from the standard, from the classical Alfred elimination technique. It is achieved with a simple minimum distance decoder, but still the analysis is quite complicated. And the converse follows from these methods. Intuitively, if the state constraint lambda is greater than or equal to than the input constraint, then the jammer can make the state sequence look like the input. Okay, here we have this symmetric channel Y1 equals X, Yn equals Xn plus Zn plus Sn. So due to the symmetry, if the state sequence is some code word, then the decoder has no way to distinguish between these two. That's why the capacity is 0 in this case. That's the intuition. So now we go back to our problem of the arbitrarily varying relay channel with sender frequency division. We give our main results. So we begin with the random code capacity. Here we define this function fg of the parameters alpha and rho, where alpha is the fraction of the input constraint that the transmitter invests in the first component of the input. Omega 1 is the constraint on the relay, and then rho is the correlation coefficient between the input component and the relay transmission. Okay, so we've shown that the random code capacity is the maximum of this function, and this actually follows from quite straightforwardly from our previous results. So this is not our main contribution in this walk. Now we go to our main contributions, which is the deterministic code bounds. Here we have the lower and upper bounds given by a maximum of the same function fg of alpha and rho, except that we have these additional constraints, optimization constraints. Okay, since for the achievability uses a partial decode forward coding scheme, so there are two steps of decoding. That's why we have these two constraints where each one guarantees reliable decoding in each step. Okay. So we've shown that the deterministic code capacity is bounded as follows. As I said, in the achievability proof, we use the techniques by Cesare and Ariane. We generalize them to the relay channel and incorporate them in the partial decode forward coding scheme. And then for the converse, we show that if the state constraint lambda is greater than this expression, then the jammer can simulate or make the state sequence look like this sum of the relay transmission and x prime. That's why if this holds, then the capacity is 0. Okay, so this is how we show the upper bound.
So just a question, partial
Sure.
decoding forward is like a hybrid of amplify and decode? Or what's the partial? I just don't want to
The partial means that the message is divided into two components, which one is sent one is decoded by the relay, and the other is sent directly. It is not decoded by the relay. That's what partial decode.
No amplify at all.
No. It's the code forward just refers to the fact that the relay decodes part of the message.
So there's nothing to gain by doing some amplification for either.
Okay, and this maybe later. I'm not sure. Okay. Yeah, these are bounds. Yeah, maybe they can be improved. I'm not saying that.
Some form of amplifier. Usually writing depending on the S1R.
Usually combine everything, compress, partial, amplify, useful.
Yeah. Okay. So now to illustrate our results, we have this figure of the capacity and the bounds as a function of the input constraint omega for the case where the relay has the same constraint. Okay, so the random code capacity is this dashed line, the blue dashed line. And then the solid lines are the lower and upper bounds. Okay, so for low values of the input constraint, we see that the upper bound is 0, and therefore the capacity is 0. Okay. Now that we look at intermediate values, we have this dotted line, which is the direct transmission bound. So we can see that for these intermediate values, we have that the direct transmission lower bound is actually better than the partial decode forward lower bound. But for high values of the constraints, our bounds coincide. Okay, so we have the capacity in this case. Now we move to the second part of the talk, where we consider the arbitrarily varying primitive relay channel. A primitive relay channel means that there is a noiseless link between the relay and the destination receiver of finite capacity C1. Okay, so one of the advantages is that the analysis is a lot simpler. Block Markov coding is not needed. You can use binning. And Kim also notes in his paper, where he introduces the primitive relay channel, that it captures most essential features and challenges of relaying, so it can be used to test new coding schemes, and practically it has the same behavior. Now we are going to show that this is not true in the arbitrarily varying scenario. That is, the primitive relay channel here is going to have a different behavior compared to the classical non-primitive relay channel. Okay, so this is a general primitive relay channel, not necessarily Gaussian, W of y, y1 given x and s, where the relay sends an index to the receiver. Okay, the receiver receives both the output y and this index. As before, the state sequence has an unknown distribution. We denote this channel by L in calligraphic font. Okay, so now, as I said, the decoder depends on both the output y and the index L. Random code is defined the same way. So now we show that the random code capacity is bounded by these bounds, which are the cut set upper bound and the decode forward lower bound. We show this using Alswed's robustification technique. Now we note that here we have a min-max form of the upper bound. And then the lower bound, for the lower bound, the maximum comes first, and then we have multiple mutual information terms. Each has its own minimum, so this is a bit more complicated of expression than the usual expression for the decode forward lower bound. And this, the order is going to be important. I'm going to go back to it. So now this allows us to determine the capacity for the random code capacity for those special cases. If the relay channel is reversely degraded and has this form, then the random code capacity is the direct transmission rate. Okay. And if it is degraded, then the random code capacity is given by the full decode forward bound, which means that the relay decodes the entire message. Okay. Now, to obtain these results, we need to use the minimax theorem, because as we've seen, there is a difference of the order of the minimum and the maximum. So on a technical level, we note that this functional, the minimum between these mutual informations, is not necessarily convex in the state distribution. It could look like this. But still, we can use the minimax theorem because it is a quasi-convex function. It satisfies this property since we've taken this marginal to be state independent. It does not depend on the state. Okay. So now we move to the deterministic code capacity, and we give these symmetrizability conditions. Okay. A channel without a relay, W of y given x and s, is said to be symmetrizable if there exists a conditional state distribution, J of s given x, that satisfies this symmetry relation. Okay, here the channel is averaged over S according to this distribution J of S condition on x tilde, and here x and x tilde switch places. Okay, so this is a symmetry. It generalizes this symmetry relation where the input and the state can be switched. Okay, so now we show that if the marginal to the relay, W of y1 given x and s, is non-symmetrizable, then the deterministic code capacity and the random code capacity are the same. So we have the same bounds, and we have additional conditions. Under this symmetrizability condition, if it is reversely degraded, then the deterministic code capacity is given by the same expression, and also for the degraded case. And then we also showed that if this channel to the combined y and y1 is symmetrizable, then the capacity is 0. So now we go to the Gaussian case. Till now, we talk about the general case for the arbitrarily varying primitive relay channel. Now we go to the Gaussian case, and we showed that there is a different behavior compared to the non-primitive relay channel. Okay, so here the relay receives x double prime plus z as before, and now the decoder receives this x prime plus s and an index from the relay. Okay, there's a noiseless link now between the relay and the decoder. So we've shown that both the random code capacity and the deterministic code capacity are given by this expression. It's not very difficult to show. And for the random code capacity, this is not very surprising, and it has similar form as what we had for the non-primitive relay channel. So for the random code capacity, we do have the same behavior. However, recall that we've seen for the non-primitive relay channel that for low values of the input constraint, the capacity can be 0 while the random code capacity is positive. Here, on the other hand, the deterministic and random code capacities are the same regardless of the value of the input constraint. That's why we have a different behavior compared to the non-primitive case, as opposed to what Kim asserted for the classical or usual primitive relay channel. Okay, so this is it. Ah, yeah.
But maybe the primitive case relates to, if I recall correctly, in random coding for ABC,
Yes,
we don't need a lot of randomness. Even
that's true.
just a little bit is enough to succeed.
Right.
So maybe the fact that you have some sorts of a link,
Exactly.
this is
The-
the intuition.
Yeah, exactly. That's true. Yeah, that's how that's the basis for the elimination technique. That you can, if the capacity is positive, in this case we have this noiseless link, then you can transmit the randomness, the index of the code that you are using. Okay, that's a good comment.
Is the Gaussian no states nothing, the simple Gaussian primitive relay channel,
Yes.
meaning input to receivers that is connected with C, is it no?
Yes, I'm talking about the case of sender frequency division. Okay, in the
No, just the simple, no states.
no,
Is it
it
simple, no states, nothing. It's simple.
it depends on what model, because you can define Gaussian relay channels in different manners. But okay,
Why
in the
one is
engine,
X plus N1, the relay X
No.
plus N2, and you have a C connection.
no,
It's
no,
not no.
no. As far as I know. No.
It's simple.
Okay, well, thank you, Professor which will be presented by Professor Antonio Pellini.
Okay. Yes. Okay. Yeah, balloons, Montgolfier. So should I start? Okay. So, okay, thank you very much for the invitation. So this is a joint work with Rami Ali and Vivek Kadampe from Penn State University and with Jaime Llorca from Bell Labs. So what I will do in this talk is overview some of recent advance in the context of multiversion coding problem. The multiversion coding problem has been formulated in order to study the cost of storing dynamic data in asynchronous distributed storage systems. So what I will do in the following, I will first review some recent results where the cost of storing dynamic data has been studied for distributed storage systems where the servers are unaware of each other's state. And next, I will actually remove this assumption, I will relax this assumption and describe some extension of this result to the case of distributed storage systems where partial server state information may be acquired. So, but what do we know with the server state information? So here, knowing the state of a server at a given time corresponds to knowing the data received by that servers up to that point. But why we are really interested in studying the cost of storing dynamic data in asynchronous distributed storage systems? Well, certainly cloud computing is nowadays the most prominent computing model, and distributed storage is one of the core components in a cloud computing environment. The primary role of a distributed storage system, as we all know, is to essentially ensure and enhance data availability. So by replicating or encoding data across multiple servers, am I right or missing the server? Okay, anyway, across multiple servers, so what I was saying is replicating on encoding data across multiple servers, user can have actually access to the data even if some of the servers fail or some of the servers are too slow to respond. So, however, distributed storage has been traditionally studied in the context of static data. So what I mean for static data? With a static library. So in this setting, let's consider this, let's for a moment consider this setting. So let's assume that we have a distributed storage systems with n server and with a static library composed by m independent file. So then, in this case, each server is going to store each file using an n-lang code so that when the user connects to any arbitrary subset of C server, is going to be able to decode the requested file. And this approach guarantees actually n-c failures in the sense that the user will be able to recover the file even if n-c server fails. Okay, but so then one possible approach to solve this problem is indeed using erasure code. So what we do, we use an NC-MDS code for each file. And in this setting, each server is going to store one code word symbol for each file. And this leads, as we know, to a storage cost per server, per file, normalized by the size of the file, which is actually equal to 1/C, where the C is the arbitrary set of servers to which the decoder needs to connect in order to decode the requested file. Okay, so unfortunately, in the application, in the context, in the application of content of distributed storage, in the context of, as I was saying, distributed computing or to modern key value store, stored data are highly dynamic due to the frequent updates. And this, for example, imply that the same file could be characterized by its multiple versions. For example, here in the slides, the file, a generic file, is characterized up to n possible different updates. So now, in this context, some new challenge need to be considered, which has not been taken into account in the traditional study of distributed storage in the static setting. The first one is definitely that data update can be very fast. Think, for example, to classical next generation service, IoT application, financial trainings, blockchain. And also the fact that there could be highly dynamic data, highly dynamics in the data, brings that an inherent asynchrony arises in the storage systems to its distributed nature, in the sense that server could actually not be located in the same data center, but actually geographically distributed. This will imply that one version of a file, a new version of the file, could not arrive to all the servers in the systems at the same time. So, but in this so dynamic setting, despite of the fast data updates, and despite of this inherent asynchrony of the systems, there is one basic requirement that is need to be guaranteed, and it's essentially that the user is going to get the latest file stored in the systems. And this property is known, this requirement is known as consistency. Okay, so now, existing approach, consistency is ensured by replication. And this leads actually to a significant cloud resource usage. If we plot the storage cost per server and per file as a function of the number of versions, you will have this essentially plot. So now, if instead you use classical MDS code, which are actually designed in the case of a static library, then you will get some coding gain here when the number of versions of each file is low, which essentially for low dynamics in the systems. But when the dynamics of the system increase, then you get the saturation of the storage cost up to the replication approach. Okay, so now the question is that, can we get a free lunch? So can we have both consistency and minimal additional resources? So in order to answer to this question, a new information theoretical approach has been formulated in 2014, which is referred to as a multiversion coding. So in this approach, users are either writer or reader, so can either write or read information in the server, the file, the updated version of the file. So user can be either writer or reader of the information. Now, essentially, there are, in order to deal with this situation, several techniques has been several protocol has been actually developed. And, but the advantage of this new information theoretical approach is that indeed this multiversion coding formulation is able to capture in its formulation both of the two problems that, both of the two characteristics I mentioned before, so specifically consistency and asynchrony. Okay, so now essentially what we have here is that due to the unpredictable nature of the propagation delay associated with the write operation, what could happen is that given this setting, each server could receive an arbitrary subset of the new version of the file. So here we are assuming that in the following, actually what we are going to do here is just focus on a single file. This will not bring any loss of generality. And we assume that the file that we intend to deliver in a consistent way to the user has been generated with the different version. So we assume also that there are, as I was saying, some propagation delay in the systems, and consequently not all servers will receive the new version not all servers will receive the new version in the system at the same time, and due to the unpredictable nature of the propagation delay, each receiver receives a subset of an arbitrary subset of this version. So how to deal with this problem? Several protocols has been developed, but the most common one is what is referred to as a quorum-based approach. So in this protocol, the write operation send a timestamp value to all the end server and wait until he get acknowledgement from CW server. And once he does this, he declares the operation, the written operation, complete. Similarly, a read operation sends a request to all end server, waits for the response of at least the CR server, and then once he gets the response from this R server, he picks from this CR server the value of the file that has the latest timestamp. Okay, so now if this is the protocol, then it's clear that for every complete pair of write and read operation, for every pair of complete write and read operation, there are at least C server, where C is equal to CR plus CW minus N, that have received the complete file that is written in storage right now in the systems and have responded to the read operation. So now, if for this protocol, given this protocol, then consistency is guaranteed, is ensured to the systems if the number of servers that define the complete reading operation and the number of servers that define the complete write operation is larger than n. This is a sufficient condition for consistency. Okay, now the question is that this is the protocol, this is the setting, which is the optimal cost. Well, before to go to the optimal cost, let me tell you that this type of protocol actually guarantee n minus the max between CR and CW failures, in the sense that the read operation, the write operation can be actually considered to, can be still be complete if n minus CW server fail. And we can still complete a read operation even if n minus CR server fails. Okay. In addition, given this protocol, you of course want that the smaller CW and CR are, the higher will be the reliability, given this sentence. So the smaller CW are, higher will be the data freshness, given the protocol, and the smaller is CR, higher will be the responsiveness of the systems, because remember that the read operation will stop when CR server has given their acknowledgement. So the responsiveness is indeed connected to CR. Of course, smaller is CR, smaller is also the overhead of the systems. Okay, so now, which is the optimal cost for these systems is essentially given by the following expression. Wang and Kadambe in 2014 were able to quantify the optimal storage cost as function of the number of versions. And unfortunately, here, even though you see a decreasement with respect to the naive MDS code at denominator, still, this, somehow this cost grows linearly with the number of versions. And in fact, so this is definitely larger than 1/c, and the grow linearly with Ni, essentially with Ni, the number of versions, tell you the impact of the dynamicity of the systems over the storage cost. So then if we plot now what did happen? Okay, so if we plot now, I don't know what did happen, changing slides, but if we plot now the Wang and Kadambe, if we plot the Wang and Kadambe plots in this one, in this figure, then if the storage cost will essentially follow for low Ni, it will follow the line, the green line, and then it will start to stay, will have a kind of stepwise behavior up to a number of versions around 14, where essentially you saturate again to the storage cost of obtained by the replication approach. So essentially, even with this technique, we still have a storage cost. Even for this optimal setting, we still have a storage cost that increases linearly with the number of versions. On the other hand, if we consider Ni equal 1, this is what we get, this singleton bound, which of course correspond essentially to the bound, to the storage cost that you get when you have a static setting, because in this case Ni is equal 1. So then the question is that, can we reach this singleton bound? Can we really get closer to this bound, which is actually the one for the static case? And why this is relevant? This is extremely relevant in next generation service. In fact, the next generation service like IoT, blockchain, financial trading, are characterized by the fact that the data are extremely dynamic. There is a very strong, stringent latency requirement, and in addition, users need to interact with the data in a real time. So this is pushing, consequently, the dynamic data to be stored at the edge cloud, at the edge, at the wireless side, or the wireless edge, leaving more the core cloud like a type of a repository. So now, the fact that the data, the dynamic data are going to be stored more and more, so in next generation service to the edge cloud, implicitly increased the distribution, the geographically distribution of our distributed storage systems. In addition, there could be type of a wireless interface at the edge cloud. All this will increase the unpredictable nature of the propagation delay of the dates update. Then consequently, designing an efficient, consistent distributed storage is extremely relevant even in the future. Without even mentioning that once you go to the edge cloud, the storage resources are extremely highly cost and have a limited availability. So all these aspects together push us even more to identify an efficient, consistent distributed storage systems. So, but how we can do, what we can explore? Then, especially for this setting that I have been described here, so when the dynamic data are stored at the edge cloud, one ingredient that actually we can exploit is the side information. So in other words, we can exploit the possibility for these servers to acquiring the state of the server. So, and in fact, we are talking here that we are mentioning the fact that this node, some of these nodes are at the edge cloud. So they can be in the proximity with each other. So some are definitely very far, others are in the proximity with each other. So nodes that are in proximity with each other, they could somehow easily exchange their state, which essentially means which data they have received until that point. Okay, so then if we want to explore the side information, so we want to explore the fact that server can somehow exchange part of the received data that they have obtained, received up to that point, two immediately extreme cases can be easily resolved. The first one is servers do not know at all each other's state, so you have a full decentralized system. Servers do not communicate. In this case, the storage cost is what we just introduced before, is grows with the number of versions. The other extreme case is the full centralized case. So each server knows the state of all the other servers. So in this case, obviously, the storage cost is 1/c, like in the static case. In fact, in this case, since each server knows the state of all the other servers, can easily establish which is the latest version of the file that has been stored in the system. And consequently, the storage cost boils down to 1/c, which is the limit of the static case. So now the question is that, can we fill this gap? So can we somehow be able to obtain, or can we understand if there are optimal gains to explore in the case a server share partial server state information. So the servers are not fully knowledge of everybody, they are not fully decentralized, but they just share some partially server state information. So only a part of the server knows, that one server knows only the state of the other server in its proximity. Okay, but talking about proximity, so when I say the idea of changing changing a state information among servers is connected, comes from the fact that some servers can be close to others. So there is a concept of a proximity, and proximity is connected to topology. So in order to establish if two servers are one in the proximity of the other one, I need to also assign an underlying topology. So as a first step, so what we did, we say, okay, let's consider a topology in a one-dimensional space. Proximity is measured in the number of hops that separate the two nodes. And we also assume that, I really apologize. And we also assume that there are no border effects. This essentially implies that what we are considering a sort of a ring topology. Okay, so now for this ring topology that I roughly explained here, so here we assume that each server is aware of the state of all the servers except one. This is quite an realistic assumption, I completely understand, but let's start to do a first step towards to what we would like to quantify. So the level of side information in the following I will denote with H. So H is the number of servers that each server is going to know. all around. Okay, so then, so essentially this implies that each server knows half of H server on the left and half of H server on the right. So then for C equal to, there are no formula. What I'm going to do, I'm going to write them. I don't know. It disappeared completely, like the plot. Yeah. Okay, let me give you the main idea. Okay, so then let's go here to this ring topology, and then you can imagine here that in reality, the storage cost is not going to increase anymore with the number of version, but is going to be constant with the number of version at the first order. So essentially, if we do an expansion for large C, we will have that the first order 1 over C is exactly equal to the static case, so does not increase with the number of version. The second order 1 over C square will increase linearly with the number of version. Now, if you go here, I was planning to compare the storage cost when you do not have side information and when you have side information. And then in this case, essentially, you will see that in the first order, the entire storage cost with no side information is just a factor of Ni, which is the number of versions. So the gain among these two approaches, even if these are, here we are pushing a very strong assumption. We are assuming that everybody knows the state of everybody else except for one. And then the gain that you get is actually equal to the number of versions. So theoretically, for a very large number of versions, you can have a very large gain. Okay, but now, is this result close to optimal? Well, yes. We had derived a lower bound that you will, hopefully you will see in the paper. Instead, we have derived a lower bound where actually you can prove that when C goes large, the storage cost and the lower bound, the storage cost, the achievable scheme that we have derived is actually asymptotically optimal. Now, this was a very baby case, a ring topology, and everybody knows the state of everybody else except for one node. So then what you can say for arbitrary topology and for arbitrary side of information. So the number of nodes that each node knows is arbitrary. You can assign, you can choose. Then what we do, okay, even here is disappeared. These were three hands shaking each other. So then the idea is that here what we introduce a graph theory in order to solve this problem and see which is the effect of the side information. Specifically, we introduce a side information graph. What is a side information graph? It's essentially a graph whose nodes are represented by the server and whose edge represent the connectivity among the server. So there is an edge between server A and server J if server A knows the state of server J. Of course, in our assumption for this study that we have done, we assume reciprocity. So then consequently, this is an undirected graph. We will not have just a directed graph between two nodes, but we will have both directions. And for example, in the ring topology, assume that each node knows only the state of the two immediate neighbors. So in this case, this dashed line, this is the ring topology, but the dashed line represents the side information graph. Because in this case, each node will know the state of these other two nodes, this will know the state of this other two nodes, and this is your side information graph. Now, assume that instead H is equal 4. So each node knows the state of this and then the state of this, and this node knows the state of this and the state of this. And this is true for all the other one. Then in this case, the side information graph is given by this graph. So, sorry? Yes, I thought so. Yeah, thank you. Yeah, I noticed that when I was building up. So, okay, so then once you introduce this side information, why you want to introduce this side information graph? Because actually, this is the only formula that remains. Okay, so because essentially the less significative in addition. Okay, so given the side information graph, we essentially what we did is we were able to connect the gain that you can get in terms of the storage cost with this quantity, which actually can be defined starting from the expression of the graph. This is a kind of measure of connectivity. Now, I'm not going to in detail of this formula, which unfortunately is the only one that is now visible, but the idea is that this formula is somehow in a compact way expressing the connectivity and consequently the level of side information that each server has. Computing this is, of course, an NP-hard problem, but we have some bound for this result. And now you should have seen how the storage costs depend on that parameter. And one more time, you will see that, again, the first order does not depend on the number of versions. The first order approximation, 1 over C. So then it's essentially, if you want, for IC, for large C, is constant with the number of versions. And then consequently, compared to the case of not exchanging side information, the gain is essentially equal to the number of versions of each file. And the number of versions of each file, it depends on the dynamicity of the system, because the number of versions that you need to take into account is connected to the delay that an entire version is going to take in order to propagate through the data storage, through the distributed data. It's amazing. There are not even the plot. This was the conclusion. If you have any question, please. Conclusion is always do PDF, probably. Yeah, you're right. No, this is PowerPoint. This is why I was concerned to put the PowerPoint in the mic. But actually, we checked the first slides and nothing was wrong. I didn't expect that a formula. Yeah, the conclusion, yes, is fantastic, right? I mean so future work, if you want, you can. It's okay. If you have any question or if solicitate any curiosity, I would be very happy to answer.
Not referring to the formula, two comments. One is in certain types of storage, like flash, for example, versions are kept anyhow because you cannot overwrite. So they stay there for a very long time until eventually in the background they erase them. So I'm not sure when you measure storage cost, some of it may be paid anyhow. Not because of problems consistency needs, just because of other reasons. Again, different kind of consideration. Sometimes copies and things like that are kept around for load balancing.
Yeah, yeah.
And again, so it's paid for, you don't need to tax yourself for it.
Yes, that I agree. Yeah, in that sense, yeah, would be hard to. But the idea here is that if you, yeah, the point is that here, if you have that is true for load balancing. But the point is that think about a static version. This is not the file, different file. This is different version of the same file. So you really don't want to do load balancing with different version of the same file, right? So you want to do load balancing with the same file. So then what the only things right now they can do is just replicate. Even if they use MDS code, and they don't actually, they just replicate this version in order to guarantee consistency. So that is true, but these are referring to not to big data center. These are referring to the fast memory, and this is why the cost this is not the big storage that you pay cheaper. This is more referred to the fast memory, where you want to have very fast read and write operation, and then consequently cost can be an issue in this case. Yeah, it's fast, I agree, yeah. Yes, 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 definitely. There is a balance there, and yeah, I agree completely.
Okay, can I start? Okay, my talk is about security identification with a path source. And I have to apologize. If you look at the contents, I didn't speak with Gerhard, but in the beginning you will see there's a big overlap with his first part of his talk. First, I will start to describe the classical communication. I remind you on the Chen picture, and I will talk about global and local randomness, for what it's useful as a resource. And also I will speak about security modeled by a wiretap channel. And then after that part, I'll switch to another picture. I switch to the picture of identification introduced by Alswede and Dück. And look what happened there. You will see there will be a huge difference between these things. And of course, of this difference, we use them for data storage, for secure identification. So we use these properties and show how we can use it for data storage. And then I will end with some conclusions. First, we start with the classical communication, the Shannon picture. So we have here Alice who want to send some message to Bob over a noisy channel, and Alice transmit a message to Bob. She used block codes, and we have a stochastic matrix, and Bob receives a word in YM. But what I want to point out is here, what is Bob's question? So in this case, Bob has to decode the correct message with a small decoding error, and his goal is finding the correct answer to the question, what was Alice's message? So his goal is to find out the message. And and we calculate what is the question of Chen was, what is the largest rate of almost free communication from Alice to Bob? And you all know then we get the message transmission capacity, which you have seen in the morning already. Yes, and then I consider here what happened if we have resources. I consider here randomness as resources, and I consider three different resources. First, like Gerhard did in the morning, here we look at local randomness, so that we can randomize encoding, and at randomness at the decoder, so that we could do randomized decoding. And also we look at common randomness, so there's a common experiment, and Alice and Bob have some common randomness. And we look what happened if we use these resources, what effects do these resources have to the coding. So first we can define also when we don't have this resource at the sender, then we have a deterministic code where we have a pair UI and DI. So UI is the code word, DI is the decoding set, and they are disjunct. So we have Bob always can make a decision which code word were sent, and then of course you have the error probability here. If you do randomized encoding, you can use probability distribution, and if you want to send a message, you just choose one probability distribution, and according to the result you send a word, and of course you have this formula here then. Of course this deterministic coding is a special case of the randomized coding. If you look at now at Shannon's theorem at the capacity, then it turned out that randomization do not help at the encoder. So what means do not help? It means that the capacity do not increase. So if you have localized, if you use a deterministic code or randomized code, the result is the same. We get the same capacity. And also if you use common randomness, then we have the same capacity. So we cannot use the common randomness in this case to increase our capacity. Then I do the same like Gerhard did. So I look at Weiner's wiretap channel here and remind you what is there. The approach, we have here Alice who want to send something over a noisy channel W, and Bob want to receive something, and there is some kind of broadcasting like it's considered by Chisa and Kerner. We have another channel V here to Eve, and Eve also want to find out what was the transmitted message. And the question is again, which is the largest almost error-free secure communication from Alice to Bob? And you saw this formula already in the morning. You have this formula here, and we interpret them already. And what's important here, we need randomized encoding just to confuse here Eve. That was also done by Gerhard in this morning. That here this randomized encoding is necessary to have this formula here. So it's again, here's it's in more detail here. Here's the definition of a wiretap code here. Again, you need that the decoding set must be disjoint, and here you have the error probability, and here I use the strong secrecy criteria. And now I switch to the identification case. So now I go to another goal. So before, as you remember, I pointed always out that Bob's question is always, what is a message? Now Alsweder and Dück, they look at another scenario. Again, we have some messages, and now Bob is only interested in message M prime, and he asks, is it transmitted or not? So he just have a fixed message. Of course, this message is not known to Alice, so she doesn't know it, because otherwise she just have to send one bit. But Bob is only interesting. What changes now? Again, we want to ask, what is the largest capacity? What is the capacity of this channel? And it turns out we get the same capacity here, but it's defined in such way that we have double exponential increase of the message set. So the message set, instead of 2 to the Cn, we have 2 to the Cn. And here again, I will say something after you see the definition at the next slide. The randomized encoding is necessary, and otherwise we just will have n is equal to the Cn again. And the idea is, the main idea is now that we don't have this property here that the di are disjunct. So we just assume that the di are subsets of yn, and we add this error of the second kind. So if you look here, the error of the first kind is the same like we have before, but the error of the second kind, this is in principle the error which comes from the coding scheme, because now we don't write that the decoding sets have to be disjunct, so they can overlap. And of course, if the decoding sets overlaps, so there could be an error because of the coding scheme. Another thing you see here, like I formulated, it's somehow I write here for all I and j, that's the maximum error. So if you want to get off, you can get rid of the randomization, of course, if you have here, if you just write here the average error. But I think for identification, it's better to use the maximal error here. So what we need is really local randomness and randomized encoding here to get this. Yes, and that's the theorem of Alswede and Dück, who did the direct proof and also what they called a soft converse, and later Hahn and Verdoux gives the strong converse also. So to overview it, so if you have a deterministic approach, you have just 2 to the cn messages, and for randomization you have this number of messages. Perhaps shortly I can give you the idea how to approach this. So you can construct an identification code from in principle from a transmission code. So the idea is you take some code C1 of length n minus, let's say, square root n, and some code, it may be the same, C2 of length square root n. So this, we assume that this code here assumes the capacity. And what we did, we consider maps T1 from the set C1 to C2 until some T big N from the set C1 to C2. And the idea in principle is that we use this part in principle only to share common randomness between the receiver and the sender. So now our messages our identification messages are the functions from 1 to n. So T1 is chosen if we want to send message 1, and Tn is chosen if we want to message n. And of course, these functions are known to the sender and the receiver. And now how we proceed, the idea is mainly, so if we want send message Ti, the sender choose the function Ti, and then make a random experiment and take some message C1, and then look to what color, mostly we call this colored. The C2 seems to be can be seen as colors of the messages. Which color have these messages in the map Ti, and then you transmit the color of the messages. And of course, the receiver who is interesting in the message I, he has the function Ti and receives the code word, which is transmitted in the first part. And then he looked to which color it is mapped, and then he checked if the color he received is the same. And if it is the same, then he decided that his code word, that his message was transmitted. Of course, you have to be carefully by choosing these functions, because we don't want that the error of the second kind is too large. Now, if we look at the common randomness here, then something interesting happened. So if we have extra common randomness here, like before, now it helps a lot. Let's assume we can create the common randomness capacity CR here from this source here. Then the capacity of this whole channel is the capacity of this part of the channel plus the common randomness capacity. So it is add just to the identification capacity. And the reason is somehow is really easy, because we can extend by common randomness just this set here. So this common randomness, what they created. And yes, and this was also the reason why Alswede thinks in the 90s, when I hear a lecture of him, it's around 94, he was thinking that the common randomness capacity is the same like the identification capacity. And for some channels it's true, but then later he found a counterexample in one direction, that the common randomness capacity is bigger than the identification capacity, and later Christian Kleinewächter gave also an example that also could be in the other direction. But these examples are always concerns about channels with memories. So now, what happened in the case if you look at the wiretap channel here now? And there we also want to check what happened now here. And here we have also some interesting fact. So if we can if we have the secure capacity, what we have before for transmitting, if it's 0, then we can also do nothing. But if the secure identification but if it's bigger than 0, then the secure identification capacity is exactly equal to the identification capacity. That means in principle we lose nothing here in this case. And you also see, and mainly here, that's the reason why I explain this construction to you, is the idea mainly is that we use for the code C2 more or less just a wiretap code, just a classical wiretap code. And because of that, we can show that then the receiver cannot identify, then the eavesdropper cannot identify any message. So we have again the message size 2 to the C times n if the secure capacity is positive. So here you see we have again error of the first kind, error of the second kind, and the security is given by we assume that the error of the first kind of the eavesdropper plus the error of the second kind is near to 1. Now we apply this to some model which is called secure storage for identification with a path source. What has happened here? So the idea here is that we have a storage cell of k cells, more or less, and we have an encoder who writes on this database, and we have a decoder who reads from the database. And also we have an eavesdropper who can also read from this database. And this model, and we have a path source, which is modeled as a discrete memories multiple source, and it puts out some xn and some yn. And we assume that the eavesdropper can have not really access to the source. He don't know what comes out here. So we make use here of this physical unclonable functions. And now we could, so we have this here again, we have the alphabet U, we have here this discrete multiple source, x and y, and now we want to define, perhaps I have to say this model was considered for the normal case where the encoder writes on the database and the decoder want to find out what have he written on the database. Now we want to do it for identification. That means the encoder writes something on the database, and later some decoder came with the same path source, and he just want to know, is a special message written on this database, and if yes or no should be the output there. And The main idea is here again to use some ideas which we use for identification. So the idea is now that we create here some common randomness, and we create a secret key. And we just have to make a very small secret key because of identification. And for the rest, we can use part of the path source also for common randomness, and this principle we all use for this common randomness thing. So we use in principle secret key construction and common randomness construction and generation, and calculate how much common randomness you can create and how much, and we have to create a secret key, and then we can apply our theory. And with this, we find out. So okay, let's be more formal. If you formally do this, we have some encoder here, and we have a decoder here, and we read out yn, and this is somehow error of the first kind. That means we decode for d. D is our message, and then we want to check with d if d is a message, and we get no, that should be smaller than some delta. And this is error of the second kind. That means we have another value than d prime, and we encode for d prime here, and we decode with d, but we get a yes. This should be also smaller than d. And this is the error probability of the decoder of Eve. So it should be the other way around, that the sum of these two errors should be bigger than 1 minus delta. And this is more or less the rate we can get. So d messages, so, d is the number of messages we have, and we do it again double logarithms here. And then we have also the privacy leakage here. In this case, the privacy leakage means because perhaps we use this path source several times. So we want that the eavesdropper don't learn too much from the coded sequence, because this one he can read to xn, which is produced by the path source. So that's the privacy leakage. And with this idea, we calculate this rate region here. So we find out weights we can have, and this is a private key leakage we get. And furthermore, what we can also do, we thought about how we can enlarge this. I gave you this property that when we add common randomness to this identification scheme, then of course we enlarge the rate. And of course this happened. So additional to this path source, we also give a public source. And when we read out them, we do some time sharing here. And of course the privacy leakage is not changed. That means if you consider this model here, we win just by adding some public randomness, some public source. We can increase the rate region, the rate we can store. So we generalize this for the identification by adding a second source, and we assume that the source is public, and we can use the public source to generalize common randomness without leaking privacy from the path source, so we can achieve a higher second order identification rates for this model, while this privacy leakage does not increase. So the conclusion, just summarizing, so what I showed is I showed somehow the difference between the Shannon picture and identification. So of course here you got much more. Here you got the message, and here you have one message, and the goal is much weaker here. You just want to know, you have one message and want to know, is this message in the message set? But you win a lot. You can have much more messages than in the Shannon picture. We also have an optimal protocol if we do this over the arbitrary varying channel or over the compound channel, and we can show that we have the same there, and also we showed a converse there, and we extend this also to quantum systems where we show that we have there similar effects. And of course, because of these properties, we also have this property for secrecy, that the secrecy in identification is more or less for free. It's already in this code construction. You have the security of identification because you can already use for C2, which I do use here. For the C2, you just use a wiretap code, and the only thing what is necessary for the channel is that the secrecy capacity is bigger than 0. Then you can also have transmit 2 to the NC messages, so much more messages than in this case where it's CS, and CS is equal, the secrecy capacity is equal to this value here. So we have another communication processing task for communication systems, and so secure data stores on public database with double exponential growth, and we show that for quantum identification, even this new task is also can be used. And what is our goal? What we did not do in this case, until now we were not able to give a converse to this authentication via path source. There is no converse until now. We just show this region which I showed you, that we can reach this region with these properties, but we have, of course, still to show also a converse for it. Okay, that was it. Thank you.
If there are no questions, then thank you again.
Thank you.
Let's move to the last talk of this session.
Okay, so hello everyone. I'm Oron, and this is a joint work with my PhD advisor, Professor Chaim Permuter. And I will talk about graph-based auxiliary random variables for the two-way channel with common outputs. So the setting that I will talk about is the classical two-way channel, as most of us know, with the common outputs, which means that the output of the channel is identical and goes back to both users. Okay. This setting was introduced by Shannon in 61, and it is also relevant today due to full duplex communication. And if to be precise in the encoding process of the two-way channel, so there are two messages, each one of them is available to one of the users, and it is a sequential transmission where at each time, say user 1 determines the channel input x1t based on the message and all channel outputs up to time t minus 1. So this is strictly causal encoding in each of the users. And the decoding process is being performed at the end of the transmission, and it is being based on the entire channel outputs and your own message that is available from the beginning of the transmission. Okay. And already from the definition of the setting, we can see that there is kind of like sequential nature for the problem. So at each time, the users can adapt their code word according to the channel outputs up to this time. Okay. So it maybe will be natural that a solution for this kind of problem will also include kind of like sequential nature in the coding, and we will see this kind. And it is known that the single letter capacity region for this problem is an open problem since Shannon introduced it in 61. Okay, but still there are some two-way channels with common output that can be solved. This is one simple example, the binary header channel. So there are two binary channel inputs, X1 and X2, that are being XORed and being fed back to both users at each time. And the simple scheme will be to transmit one bit of information at each time by each of the users. So for example, at time 1, X1 just transmits one bit from the message, the same one for X2, and at each time, both of the users can decode a bit of the other user by XOR the channel outputs with your own transmitted channel input. Okay? And it is not difficult to show that this is the achievable region, which is also optimal by simple cardinality arguments. And the idea behind this specific example falls under a little bit broader framework that Shannon already derived in his original paper, which is called the Shannon's inner bound for the case of common outputs. Okay? So this is an inner bound, and the focus here is to see that there is an independence between the channel inputs. Okay? So the joint distribution is the multiplication of two independent px1 multiplied by px2, and this includes the capacity region of the previous example, the binary header channel. And the coding for this region is a simple IID argument, so each message is being coded into an IID codeboard X1 and X2 respectively. And in simple words, what we can say is that the users ignores the past channel outputs. So they have access to YT-1, but they still ignore it and just encode based on their messages. Okay, this is the only information that they use. So in Mac with feedback, you need to decode based on the channel outputs only. But here, each user can decode based on the channel outputs and your own message. Okay, so it is a little bit more difficult. Okay. I think that if you consider such a coding for the Mac with feedback, so you will have also on the sum rate constraint. Okay, X1, X2, and Y. This is the main difference. And there are many works who showed that this kind of simple coding is tight. For example, which means that it achieves the capacity. For example, the Gaussian channel, the exponential channels, and there is a list of sufficient conditions that show that this region is optimal for those cases. But in general, the Shannon coding is not optimal, okay, which means that we need to maintain kind of cooperation or adaptation based on the channel outputs. The full capacity region was derived by Kramer in his PhD thesis, and it is given by the conditional directed information, which is a multiletter expression. Okay, so we have that each rate is bounded by this sum of mutual information, and also the focus here should be on the joint distribution, which shows that each of the users need to maintain an exhaustive dependence on all the history information that is available to you, which means that the user 1, X1T, needs to depend on the entire channel inputs up to this time and all channel outputs up to this time. This is what achieves the capacity. But it is not computable. This is a multiletter expression. By the way, the Shannon inner bound can be revealed if we just restrict the input distribution to be the multiplication that we've seen earlier, and we know that cooperation is necessary. So we have the two extremes. The one extreme is the Shannon inner bound, which means that the inputs are independent, okay, and do not depend on channel outputs. And on the other extreme, there is the capacity region that need to depend on the entire information that is available to you, okay? And when we wanted to derive an inner bound, we looked for some intermediate point where they use some information of the past that you have, but still that you can simplify the inner bound to have a single-letter expression. Okay? So the approach that we took is based on something that we call the Q graph, okay, which is an irreducible and directed graph that has the property that for each node, its outgoing edges are labeled with all possible labels from an alphabet L. For example, if we fix an output labels alphabet of 0, 1, and question mark, then this is a Q graph, since in the output of Q equals 1, we can see one time 0, 1, and question mark, and the same for the other node, we can see exactly one time 0, 1, and question mark, which is the entire labels alphabet. Okay? So this is the definition, and it is used in order to define a mapping from any sequence of labels into one of the nodes on the graph. So for example, if we begin in this node and we receive a sequence 0, 1, 0, then we will do a self loop, 1, and then 0, and the mapping will return the first node in the graph. Okay. So this is how we use it, and for the two-way channel, we will take two different Q graphs. Each one of them will be used by one user, and the labels alphabet of the first user will be x1 times y, and the other Q graph of the second user will be the channel input alphabet of the second user times y. Okay, so they use both information that they produced in the past and also based on the channel outputs. Okay. And with this definition of the Q graph, we could show our main result, which is an inner bound. And it states that for any fixed Q graphs Q1 and Q2, the following is an inner bound, and the joint distribution is the one that depends on the Q on your own Q graph. So x1 will be dependent on its Q1, and x2 will depend on Q2. And the random variables Q1 and Q2 are the one that the graph-based auxiliary random variables are computed. The entire joint distribution is computed with respect to some stationary distribution. Okay, so we fix an input distribution, and then we compute the stationary distribution that is affected from the inputs, and then we evaluate this inner region. And the stability condition is something technical of Markov chains that will be illustrated through an example. Okay. Okay. So the Shannon bound is contained in this inner region, and we were wondering whether it is strictly larger than the Shannon inner bound, whether this graph-based cooperation can improve the Shannon approach. And to this end, I will show another simple example, which is called the binary multiplying channel. And also here we have binary inputs that are being multiplied and being fed back. Its multiplication are fed back to the users, and this is a very old and classical example of a challenging two-way channel that was suggested to Shannon by David Blackwell, who was very good at finding difficult and simple problems. And by evaluating the Shannon inner bound, we get that the equal rate point is 6169. Okay. Schalkwijk came up with a simple scheme that showed that this can be improved, and he showed that the equal rate can be improved to 6191. The number is not the issue, but the idea that cooperation can improve was captured by his fundamental scheme, and he also improved this rate by using bootstrapping, but this is not the point. We are just looking for an example where we show that our region is strictly larger than the Shannon inner bound. Okay. So we took the Schalkwijk 82 scheme and presented it on two Q graphs. So we have Q1 on the left, and we have Q2 on the right. Each one of them is being used by one user only, and their labeled edges are labeled with the X and Y. Okay, and I will show an example how the transmission or how the encoding process occurs. So let's say that both users begin at Q equals 1. Okay, so both of them begin at the extreme nodes, and say that they both transmit X equals 1. So the output is their multiplication is also 1, and both of them are going by the self loop to the same node. Okay. And at the same time, since the output was 1, then the user 1 knows exactly what is the graph node of the other user. Okay, so it also knows like the encoding state of the other user. Yeah.
But another example is where the first user transmits 1 and the second user transmits 0, then the channel output is 0. So user 1 is now at q equals 2, and q2 is at is in node number 3. But at this point, the first user is like the strong user, since it also knows the graph node of the second user. But the second user doesn't really know what is the node of the first user. Okay, so it maintains kind of like an estimation on the graph node or the encoding state of the other user. And the stability condition just verifies that given your own node, you maintain a stable estimation over the graph of the other user. This is like the main idea. Okay. So if we fix the previous two Q graphs and the following input distribution, we can show that it satisfies the stability, the Markov conditions that we needed for our theorem, and then we can evaluate the expression of the inner bound. So this is just a schematic derivation. The channel is deterministic, so the mutual information boils down to this conditional entropy. And once we compute the stationary distribution, the other terms can be evaluated very easily. This is a single letter, and I will skip the technical steps, but the main idea is to compute the stationary distribution on Q1 and Q2 on the graphs. So by continuing this derivation, we could show that the following equal rate is achievable by the general inner bound. And not very surprisingly, it achieves exactly the Schall-Quick 82 equal rate point 6191, which is the better number between of the two from the previous slides. And this can be extended to derive the entire achievable region, not only on the equal rate point, by taking a different alpha beta. And I think that it is quite interesting that our general framework of like Q graph or something that was not known at the Schall-Quick time captures his fundamental scheme that was one of the breakthrough, I think, in two-way channels, where we showed that the channel is not optimal for the two-way channel with common output. Okay. So to conclude, we restricted the cooperation or the operation of the encoders to two Q graphs and identified sufficient conditions, the stability conditions, in order to show that the following single letter is an achievable region, which is strictly larger than the Shannon's inner bound, which means that cooperation on graphs can improve the Shannon bound. And there is also some ongoing work on the two-way channel. So we are trying to construct a posterior matching scheme for this inner bound. Then we will have a simple scheme, low complexity scheme that will achieve this inner bound. This is one direction. We are also looking for graphs that will improve upon the Schall-Quick scheme. Okay. And the last point, which is, I think, the most interesting but also the most challenging out of these points, is graph-based upper bounds. We have a previous work on channels with feedback and memory, where we showed an upper bound on the capacity using the same idea of Q graph. So we are trying to extend these ideas that we have in the encoder-decoder framework to the two-way channel, where we have two active users. Okay. And that's it. Thank you. No, so I was trying to embed the bootstrapping in the general in the inner bound. It is not quite clear. I think even if we do that, it will not be a nice single letter expression. It will be much more complicated.